In this video, we're going to talk about Riemann sums, and we're going to use them to approximate areas under curves using rectangles. So this is how it's going to go. You're going to estimate the area under a curve, and again, what we mean by under is between y equals f of x and the x-axis, right? And y equals 0. Really between those two curves. All right, and so what we're going to do, you've got a curve, y equals f of x. You're wanting to find the area between the curve and the x-axis over a particular interval in the domain, say x is a and x is b. So the question is, what on earth is this area? Right? What on earth is that area? What you're going to do is you're going to break up this interval, BA, into n subintervals. Then I'll have n rectangles. Right? How are you going to get them? You're going to take the whole length of the interval, which is b minus a, and then divide by the number of rectangles that you have, the number of subintervals you have, and that'll give you this little tiny change in x. That's the width of each rectangle, or we could say equivalently to width is base, right? Base times height, or length times width, right? That's the base of each rectangle. And then we're going to calculate the area of each sub-rectangle, either using left endpoints, right endpoints, or midpoints, in fact. And we're going to do an example. Right, so we're going to break it up and we'll get the area of that rectangle, the area of that rectangle, and so on. All right. So let's go ahead and do an example. All right, so example 2, estimate the area under the curve square root of x. That's what I have graphed here for us. Y equals, or f of x equals square root of x over this interval in the domain you see from 0 to 4. So we're asked to find this area, or estimate it rather, and we're asked to estimate it in a particular way with n equaling 4, so there are 4 rectangles, and we will be using right endpoints for each subinterval of the domain to calculate that height of each rectangle, which is a function value, right? That's a y value. That's a function value. All right. So one estimation, and because I'm using right endpoints, often we'll do an R for right endpoints, and then I'm telling the reader I'm using 4 rectangles here. What is that going to be? I think drawing it first is the way to go. So the length of each interval, since the whole domain here is going from 0 to 4, we have that our little tiny change in x is our right b minus a all over n. It is 4 minus 0 all over 4. It's just 1. So all of these are my little tiny changes in the domain. They're just the width, they're just the base of all those rectangles. All right? They all happen to be 1. And now, when I look in my first subinterval between 0 and 1, because I'm doing right endpoints, I'm going to choose 1 to be the x value that I want, and then go find f of 1 to get the height of my rectangle. Between 1 and 2, I'm going to choose 2, and then f of 2 is going to be the height of my rectangle. And then between 2 and 3, I'm going to choose the right one, 3. F of 3, that's going to be the height of my next rectangle. And then lastly, between 3 and 4, I'm going to choose the right one, 4, and F of 4, that height is going to be the height of my rectangle. All right, so between between 0 and 1, I'm choosing 1, F of 1, square root of 1 is 1, that's the height of my rectangle. You can see that this is going to be an overestimation of the area under this curve, square root of x, because look at all this area right here that I'm including that's not there. For my next rectangle, I'm going to use the green height. For my next one, I'll use the blue height, and that last one, the fourth one there, I'll be using that pink height. This is a very crude estimation of the area between the curve y equals square root of x and the x-axis bound by those vertical lines x is 0 and x is 4. Right, so what does this look like? They're all heights times bases. F of 1, my yellow height, times your little change in x. Plus, then we're going to add on my green height, F of 2, times your little change in x, which we know to be 1. Right? So right here, that's representing the area of this rectangle. And right here, that's representing the area of this second rectangle. And I'm adding it up. The whole is approximately equal to the sum of its parts. The area of my third rectangle, well, the height we're going to use F of 3 times my base, little change in x. And then this product, that height times that base, is right here. That's the area of that rectangle. And then lastly, we're going to add on the area of the fourth rectangle. Its height is F of 4. Little change in x, that's the length of the base of that rectangle. All right. F of 1 is 1. And your little tiny change in x's are all 1. Obviously, if we were really wanting to go after, like, get a good approximation, 4 rectangles is not that good, right? We'd want to have a lot more than 4. But I want us to not have to do too many rough calculations here. Just get the concept across. Oh, and yellow. So yellow is 1, my little change in x is 1. Plus my green height, F of 2, is the square root of 2, right? When x is 2 on the square root function, the y value is square root of 2. Times your little change in x, which is 1. Plus, lastly here, no, not lastly, we got 2 more. F of 3 is square root of 3 times your little change in x, which is 1. And then adding on the area of my fourth rectangle, we've got square root of 4, which is 2. 2 is the height of my fourth rectangle, and its base is a 1. All those little change in x's are 1s. All right, so that gives me 1 plus the square root of 2 plus the square root of 3 plus 2, which is about 6.15. There we are, done. R of 4 just means I'm using right endpoints, and the 4 is saying I have 4 rectangles here. We're done. All right, now let's do it again, but now let's use left endpoints, right? So between 0 and 1, I'm going to choose 0. F of 0 is my first height, which feels really, really strange because f of 0 here is 0. So basically, I'm saying 0 times 1 is 0. I'm estimating the area for my under the curve just right here is actually 0. Huge underestimation. Between 1 and 2, I'm going to choose 1 to be the height, or f of 1 to be the height of my second rectangle. F of 1 is 1. Between 2 and 3, again, we're doing left endpoints, I'm going to do 2. So f of 2, which is the square root of 2, that green height right there, is going to be the height of my third rectangle. And then between 3 and 4, I'm going to use 3, f of 3, which is the square root of 3, will be the height of my fourth rectangle. All right, so just a little notation. I'm using left endpoints. We've got 4 rectangles. What is this Riemann sum? Approximating the area under this curve is by adding up the area of the first rectangle, which is 0, right? It's f of 0 times a little change in x. Maybe we'll even put, how about an orange dot right there? F of 0, which is 0, times a little change in x, plus, then for the next rectangle, what did we use for the height? We used f of 1 times my little change in x for my base. Then we're adding on the area of my third rectangle. For its height, we're using f of 2. Base, change in x. And lastly, for my fourth rectangle, its height, we're using f of 3. The blue height right there. And the base is a little change in x. All right. And again, the 4 is just telling me that we've got 4 rectangles here. F of 0 is 0. Times my little change in x is 1, which is 0 times 1, which is 0. That's why there's no first rectangle there. Plus f of 1 is square root of 1, which is 1. Times my base. Plus f of 2 is the height of my next rectangle, which is square root of 2. Times your little change in x, the base of that rectangle, which is 1. And now lastly, f of 3 is the height of my last rectangle, square root of 3, times my little change in x, which is 1. Oops, blue. All right. And I've already calculated this for us. 4.15. All right, and we're done. Okay. So notice here that my right endpoints ended up being overestimations because my function was increasing here. When I'm choosing a right endpoint, if my function is increasing, this height is going to be bigger than that height. The green height is bigger than the yellow height, right? So we have overestimations. And then my left endpoints ended up being underestimations, right? Look at all these areas that I'm not even including. Perhaps something that would be even better is if we used midpoints. So instead of between 0 and 1, picking either 0 or 1, what if we pick what's right in the middle there? What if we pick a half and then go find f of a half, which is square root of a half, and use that to be the height of my rectangle, right? And between 1 and 2, what if we picked, 3 halves? And between 2 and 4, 5 halves, right? And between 3 and 4, pick right in the middle, 3.5, 7 halves. Then our approximation would be better. And we're still only using 4 rectangles. So little notation, M for midpoint, and then 4 because we got 4 rectangles here. So perhaps a better approximation would be to find the area of these 4 rectangles. You can see how I'm counting some area here that I don't want to, but then I'm not counting some area there that I do, and those are kind of evening each other out. That's happening throughout here. All right? All right. So I'm going to use f of a half for the height of my first rectangle. And my little tiny change in x still happens to be 1. So we're just going to write change in x here. And then plus the height of my next rectangle, I'm going to use f of 3 halves, or f of 1.5 if you prefer. Base, little change in x. Height of my, how about red? Height of my third rectangle, I'm going to do f of 5 halves times my little change in x. And then for my last one, the height, I'm going to do f of 7 halves times my little change in x. All right. And you can see why perhaps a calculator would do, or a computer would be doing a much better job than a human being to do, right? Because ideally we want to have how many rectangles? More and more and more. In fact, infinitely many. All right. M4, using midpoints for the heights here, we get 5.38, right? Notice that that is doing a bit better job. Here we had an overestimation, underestimation, and then this one's evening out a little. But it's still not saying the exact area yet. We're close.